My dear students, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I would like to welcome you all to our International Physics webinar. So, good morning to all here in Bangladesh, and a very good evening to all those who are watching this program live from USA. So, hope you are well and safe from Corona pandemic. Today, it's our 141st International Physics webinar, and we have successfully completed our 140th International Physics webinar, including two Nobel laureate speakers. So as we know that we are staying in a corona pandemic situation and we cannot continue our normal academic program since May 2000, since March 2020, and it's very difficult for us to continue our normal academic program. So we have started our online program. I think you have already come to know that Department of Physics, Pabna University of Science and Technology has started its online program, including online international physics webinar. So today is very important day for our department. Today I'd like to welcome you all to a joint session between the Department of Physics, Pabna University of Science and Technology, and the Department of Physics and Astronomy, Louisiana State University, Louisiana, USA. And we have with us here today Dr. George Pullin, sir, Professor and Hearne Chair of Theoretical Physics, Department of Physics and Astronomy, Louisiana State University, Louisiana, USA. And he has already connected with us through online. So I'd like to welcome our speaker, sir. Good morning and good evening to your part. Thanks for accepting our invitation, sir. So it's our pleasure to host you in our International Physics webinar. So for those who are new, I'd like to inform that we have divided our webinar into three parts. First of all, I'd like to introduce our speaker with all of you, and then our speaker will deliver his piece. And at the end, we have a discussion session. In that time, anybody can join with us. And you can ask question by commenting also. So I think you have already come to know the title of this today's International Physics webinar, and title is Loop Quantum Gravity Overview and the Recent Development. And our speaker is Dr. George Pullin, sir, Professor and Hearne Chair of Theoretical Physics, Department of Physics and Astronomy, Louisiana State University, Louisiana, USA. So George Pullin, sir, is a Hearne Chair in Theoretical Physics at the Louisiana State University. He is well known for his work on black hole collision and quantum gravity. George Pullin attended the University of Buenos Aires Electrical Engineering for 2 years before leaving for Institute of Balseiro in Argentina to finish a MSc in Physics 1986. Then he moved to the University of Cordoba to pursue his PhD, which was submitted in 1988 to the Institute of Balseiro. His advisor was Reynaldo G. Glaser. He moved to Syracuse University in 1989 and the University of Utah in 1991 as a postdoc. He joined the faculty of Penn State University in 1993, where he was promoted to associate professor in 1997 and full professor in 2000. In 2001, he moved to Louisiana State University, where he is the co-director of the Horace Hearne Institute, along with Jonathan Dowling. Pullin's wife, Gabriela Gonzalez, she is also our another speaker. On May 10th, she will deliver her speech in our International Physics Forum. So I'm happy to share with all of you that. Is also a gravitational physics researcher. She and Pullin met at a gravitational physics meeting in Cordoba, Argentina. Pullin and Gonzalez spent 6 years living apart while Pullin was at Penn State and Gonzalez held a position at MIT, a situation that was resolved when they both were hired by Louisiana State University. Pullin's book with Gambini, Loops Not, Gauss Theories and Quantum Gravity, surveys the state of the Earth in loop quantum gravity at the time of the publication. Reviewer Jerzy Lewandowski writes the book should allow people from outside the loop circle to gain access in the current state of the Earth. But most of all, it allows experts within this wide field to learn more about the original construction, which were invented and applied in quantization of gravity by Gambini and Pullin themselves. Chris Isham adds that this is the most valuable addition to the scientific literature, while Hugo A. Morales call it useful for an immersion in the subject. Pullin's most cited research paper on non-standard optics studies the propagation of light within the theories of loop quantum gravity and shows that these theories lead to prediction of behavior different from the Maxwell equation for light propagation in classical physics. Pullin, Gambini, and Burns Brusman also wrote a series of papers that make an important connection between the knot theory and quantum gravity by showing that the Jones polynomial can be used to solve a quantum form of Einstein equation. Pullin is also known for a series of papers on the theory and numerical simulation of colliding black holes. Pullin's early work on subject, including his second most cited paper from 1994, involves the close approximation in which a pair of nearby black holes is treated mathematically as a single non-spherical black hole. Since joining Louisiana State University, his work on this area has been based instead on supercomputer simulation. Another pair of his papers studies a simplified mathematical model of the radiation emitted when a star collapses into a black hole and shows that it compares favorably to numerical simulation. Awards and honor in 1998, the John Simon Guggenheim Memorial Foundation selected Pullin as a Guggenheim Fellow, and in 2001 he won a Fulbright Fellowship to visit Universidad de la República in Uruguay. In 2001, the American Physical Society honored him with the Edward Bouchet Award, recognizing him as a distinguished minority physicist who has made significant contribution to physics research. He is a corresponding member of the National Academy of Science and the Science Uruguay and Mexican Academy of Sciences, the Argentine National Academy of Sciences, and the Latin American Academy of Sciences, and a fellow of American Physical Society and of Institute of Physics and the American Association for Advancement of Science. You can see his Google Scholar ID, and his citation is more than 9,000. And this is his Inspired Hep ID. This is his current publication. So thanks for all of your patience. Now it's time to go to our speaker. So sir, thanks again for accepting our invitation, sir, and for joining with us. So it's your time. You can start your session, sir.
Okay, thanks a lot for the invitation. Good morning to all of you. I thought I would tell you a little bit about loop quantum gravity, what is it, and some recent developments. So this is the plan of the talk. We'll first say, what are we talking about here? What is the problem here? What is the problem with quantum gravity? We'll introduce what loop quantum gravity is, and we'll talk about two applications in cosmology and black holes. And then we'll finish with a summary. So the first question here is, why do we want to quantize gravity? So our current understanding of nature is that there are four fundamental interactions: the strong, the weak, the electromagnetic, and the gravitational interactions. And we know that processes involving the strong, weak, and electromagnetic interactions require the use of quantum mechanics to describe them. Do we really need a quantum description for gravity as well? Well, not for practical reasons. Gravity is a weak macroscopic force. The electromagnetic strong and weak interactions are important at the microscopic level, where we know that quantum mechanics is needed to describe things. The microscopic level, gravity is very weak. The force of gravity between two electrons is 10 to the minus 44, the force of electromagnetic repulsion between them. So there is not really a practical reason to quantize gravity. Gravity is a force that is relevant in the macro, in astronomy, and big stuff. However, we need to do it for conceptual reasons. We do not know how to couple classical and quantum mechanical theories consistent. You can't leave a theory classical living with quantum theories. The reason of this is you all probably learned in your quantum classes that quantum theories do not have values for their magnitudes until you measure them. It's not that you don't know the values. Classical theories, you also don't know the value until you measure them. In quantum theory, the value doesn't exist until you measure them. Now, how are you supposed to couple a theory that needs values for its variables all the time with a theory that only has values when you measure them? We don't know how to do it. If you want more details about this, Carlip has a paper that if you try to couple them, you'll lead to inconsistencies. So we need to quantize for conceptual reasons, and yet we have no experiments to explain. There's no experimental situation we know about that needs both quantum mechanics and gravity. So you would think, well, theorists should have a field day here. You know, they could produce theories galore because there's no experiments to constrain them. However, this is not the case. In spite of the situation, we do not know of a single theory of quantum gravity that people agree upon. The reason for this is that when we talk about gravity here, we're not talking about Newton's gravity. We're talking about our modern understanding of gravity that is described by Einstein's theory of general relativity. In Newton's theory, gravity is described by a force. You have two masses, they attract themselves by a force. In general relativity, the effects of gravity are accounted for by a deformation of space-time. The Earth doesn't go around the Earth. The moon doesn't go around the Earth because there's a force pulling on it. It goes around the Earth because the Earth deforms space-time, and the natural trajectory is not a straight line anymore. It's a curved line. So to quantize gravity, really, is to quantize space-time. And it means that we're going to try to do something that we never did before. For all the other three interactions we're talking about here, space-time was fixed, and there was a force living on them, and we quantized the force. Here we're talking about quantizing space-time itself. And so it's not surprising that we're having trouble because we never did this before. So what goes wrong? Well, the usual way to quantize field theories is to use perturbation theory. So you start with a theory without interactions, which is easy, the free theory, and then you turn on the interactions as small perturbations. In principle, looks like this would work for gravity. The only physical constants involved are Newton's constant, the speed of light, and h bar, Planck's constant. These can be combined to give a unit of energy, which is the Planck energy, which is 10 to the 19 GeV. This is humongous by particle physics scales. So it would seem that for ordinary scales of ordinary particle physics, everything would work okay because this energy is so large that indeed you're dealing with small perturbations. So the way you do perturbations is you expand the e to the Hamiltonian in powers of the coupling constant, and this leads to the usual Feynman diagrams. I drew the diagrams here that correspond to electrodynamics, but you could write similar diagrams for gravity. These type of calculations usually lead to infinities, and there's a process to deal with those infinities known as renormalization. In the case of gravity, however, the procedure fails. The theory is what is known as non-renormalizable. Now, some people believe that this failure of the perturbative treatment is a problem. It shows that the theory we're trying to quantize is probably wrong. They have an example of this in the past. In the 50s, Fermi had a theory for the weak interactions called the four-vertex theory, and it had similar pathologies. But it turns out that the Fermi's theory is not the true theory of the weak interactions, but it's just an effective theory that approximates the true theory at low energies. The true theory is electroweak theory, and that theory is renormalizable. So could something similar be happening in gravity? Those who take this point of view believe that Einstein's theory is really not the true theory of gravity, but it's just an effective theory valid at low energies, and that there's a more fundamental theory underlying it that explains things. A leading exponent of this is what is known as string theory. People who believe that string theory describes nature believe that that is the theory you should be quantizing, and general relativity is just a low energy approximation. String theory has other ambitions as well. It wants to explain other interactions as well as gravity. This sort of controversy has sort of split the community into two fields. One field of people feels this way. Another field of people feels a different way. This was captured by Physics World, the British sort of magazine, with this sort of diagram that says people go into string theory or go into loop quantum gravity or other directions when they try to approach quantum gravity. The other group of people, and the point of view that we're going to take today, is we don't really know that Einstein's theory is wrong. In fact, because it's so different to the other theories, it's not entirely surprising that we have a problem. Perhaps what we need to do is we need to sort of examine better the way we're quantizing theories. Perhaps we have to try with some new techniques. And these new techniques we're going to use are what are known as loop-bound gravity. So what is this? So how did this start? So Abhay Ashtekar, who was originally from India, at the time he was at Syracuse University in 1986, showed us how we could write general relativity with variables that are similar to those of Yang-Mills theory. Yang-Mills theories are the theories that describe the strong, the weak, and the electromagnetic interaction. And Yang-Mills theory essentially is like Maxwell's theory, but it has several electric and several magnetic fields that interact with each other. Now, when one wants to quantize theory, typically you want to write them in what is known as a canonical way. So we need to introduce a Hamiltonian and canonical variables. The idea in general relativity is you break space-time into space, so this surface here will be space, that evolves in time. And when you do canonical theory, you need your Q's and your P's that are equivalent to your X and your X dots, so to speak. In general relativity, the Q would be the geometry of this spatial slice. That's why I put a 3 there, because it's 3-dimensional. Space-time is 4-dimensional, but space is 3-dimensional. And you need a canonically conjugate variable that plays the role of X dot. In this case, it's called K. It's a tensor. It's called extrinsic curvature. The details don't matter too much, but it gives you an idea of how this spatial geometry sort of evolves in time. What Ashtekar proposed was to replace these variables. Instead of using the 3 metric, the 3-dimensional metric, you use 3 vector fields. That's why there's an extra index on them that goes from 1 to 3. This is just a regular vector index. This goes from 1 to 3, telling you there are 3 of them. And the canonically conjugated variable, he called it A, behaves pretty much like 3 vector potentials of a Yang-Mills theory. I told you that in Yang-Mills theory, there are multiple electric fields. That's why I call this suggestively E. There are multiple of them because this goes from 1 to 3. And there are many vector potentials because this goes from 1 to 3. So general relativity, written in terms of these variables, looks like a special type of Yang-Mills theory known as SU2, which, by the way, is the Yang-Mills theory that describes the weak interactions, with some extra equations, with some extra constraints. This, when it was done in 1986, more than 30 years ago, opened a lot of hopes that the techniques that were used to quantize Yang-Mills theory could be applied to gravity. But if you think for a second, that sounds a little bit contradictory to what I was saying 2 slides ago, because I told you that the reason we have problems with gravity is because it's very different than ordinary theories. Now I'm trying to tell you that just changing variables is going to make the same. Well, no. So these original hopes were a little bit overstated. Turns out the initial hopes were a bit too optimistic. When you look at things in detail, most of the techniques that you apply for Yang-Mills theory cannot be applied to gravity precisely because it's a different theory. However, some techniques have proved useful, and one of them is the use of loops. Now, when I start talking about loops, a lot of people get lost because most physicists are not accustomed to dealing with loop variables. So let me start slowly and tell you that you all have dealt with loop variables in your physics careers. So let me go very simple, go to Maxwell's theory. We all know the curl theory that says that if you take a vector potential and you take the circulation along a closed loop, this is equal to the surface integral of the magnetic field along a surface whose boundary is this loop. That is what this means. This loop is the boundary of this surface. Now, if I were to give you the value of this quantity, of the circulation, the left quantity, for all possible loops, it is tantamount to giving you B. I hope there are no mathematicians in the audience because the way physicists prove this is very simple. If I were to take very tiny loops, this right integral, of course, the surface integral just becomes a product, just becomes B dot ds. And obviously, if I give you this value for all possible small loops, I'm giving you B. So giving the value of this loop-dependent variable, because this thing depends on a loop, for all possible loops gives you all the information you need to know about the magnetic field. Well, it turns out similar results hold for the vector potentials that appear in Yang-Mills theory. As I told you, there's several of them. So the equation in question is a little bit more complicated than this one, okay? It's not exactly like this written here, but it's very similar. The path-dependent quantity, the thing on the left, for that case is known as the holonomy. If you ever hear seminars, you'll probably hear that word. And there's a theorem known as Giles' theorem that says that if I give you the value of the left quantity, the holonomy, for all possible loops, I give you all the gauge invariant information that you have in your field. So you can reconstruct entirely your field in terms of these loop variables. So these loop variables are an alternative way of describing electromagnetic or Yang-Mills fields. So this is what led some people to believe that you could actually build a quantum representation for all these theories, for Yang-Mills, for gravity, based on these variables, based on loops. So this representation was first proposed by my collaborator Gambini and Antoni Trias for Yang-Mills theory in the 1980s. Now, at that time, we did not know, or no one knew, how to write gravity in terms of variables like that. But when Ashtegar introduced these new variables for gravity, then it led Rovelli and Smolin to follow the same path and to try to write a quantum representation for gravity purely in terms of these functions of loops. So it would sort of look like that. That would be your quantum state. That is one of your kets. Your ket for your theory is a function of a loop. Now, there's an important point I need to bring up here, and is that in gravitational theories, everyone heard that general relativity is invariant under any coordinate transformation. You can pick any coordinate you like to describe the theory, and all of them are equivalent. There is an equivalent way that mathematicians use to describe this situation, which is instead of having a space-time and having some coordinates and choosing different coordinates, what you do is you keep your coordinate fixed and you move your space-time. Obviously, the two pictures are equivalent. Moving this or moving this is the same. So what mathematicians usually say is that these theories are invariant under what is known as diffeomorphisms, meaning you can move your space-time around. And if you think about that, this point of view is kind of the most natural here. You see, a theory of gravity is a theory of a geometry, meaning until you solve your theory, you don't know what your geometry is. The only thing you have is a manifold with some points on them. Until you put a geometry on that manifold, all those points are equivalent. It's like if you were in a boat in the middle of the ocean at night, and it's a cloudy night, and you're far away from the coast. You can't tell where you are. All the points of the ocean look the same to you. You can move your boat around and make no difference. Everything would look the same to you. Well, similarly, when you have one of these theories where gravity is given by a geometry, until you put a geometry in space-time, all the points are the same and you can move them around. Now, if you can move the points around, it means you can move the loops around. Obviously, we're doing physics here. We want to have differential equations, so we don't want to do crazy motions. We want our motions to be sort of differentiable, meaning if 2 points are close here and I move them around, they're still close down there. That's why these things are called diffeomorphisms. Morphisms are just are maps, are motions, but diffeomorphisms means, well, whatever is closed still is closed. So what you need is our functions of loops that are such that if you move the loops smoothly around, they don't change. Mathematicians have studied this for a while, and these type of functions are known as knot invariants. Now, this group of people down here, whose initials constitute the word lost, prove this thing called the Last Theorem. Again, it's not because it's lost, but because it's the name of these four people, and Hans Fleischhacker was involved. That's why it's called Lost F. And what they showed is that if you impose that your states are invariant under this type of smooth motions, the inner product that you can introduce, the sort of expectation values that you can take, is essentially unique. This inner product is mathematically quite elaborate, but remarkably, I can explain it to you with a picture. The inner product is such that if you have two states based on loops that can be deformed smoothly into each other, like these two, they are the same. So the inner product doesn't care if you have this or that, because these two can be deformed into each other. Whereas these two, although they kind of look close, they're not, because they have that little knot there. And you can't undo that knot unless you cut the loop. You can't smoothly make that knot go away. So although these two loops kind of look almost the same, except for that, they're infinitely apart from the point of view of this inner product. This inner product was introduced by Ashtegar and Lewandowski, and although, again, I can explain it to you with a picture, if you want to understand the mathematics behind it, it's quite elaborate. They publish papers in, Journal of Functional Analysis and other highbrow mathematic journals with all the details, but the essence of the product can be captured by this picture. So in terms of this Hilbert space, so once you have a Hilbert space, you can start talking about your quantum theory. If you have just wave functions, you don't have a quantum theory. Until you have an inner product that allows you to compute expectation values, you can't do anything with a quantum theory. You can't compute any sort of predictions of the physics out of it. Once you have an inner product, you can. So with this inner product, people went on and started building a quantum geometry. That is, since this is a theory of a quantum spacetime, we now have the quantum states to do it. We build our physical observables. So this unique kinematics was first constructed in the 1980s. It has high mathematical precision, and it provides a notion of a quantum geometry. It replaces the Riemannian geometry that was used by Einstein for his general theory of relativity. And there were many authors involved, and I've listed some of them here. The quantum states are known as spin networks. So instead of just being functions of loops, as I talked about, it's a little bit more complicated because, as I mentioned, these theories has many electric fields, many vector potentials. So I told you that, the Stokes theorem is a little bit more complicated. You need to keep track of all that by putting a number associated with each loop. That number is known as color. And the states are loops with intersections with numbers associated with each line. These are known as spin networks. The fundamental excitations of the geometry therefore become one-dimensional. So at the Planck scale, when things are very quantum, you have a polymer geometry, and the continuum geometry that we're ordinarily accustomed to living with arises only in the coarse grain approximation, when you're at very large scales, and all these little details are irrelevant, and you just see a smooth classical geometry. Each of those lines can be thought of as carrying a quantum of area. If you choose a surface, its area will depend on how many lines thread it and its color. So, for instance, if I have a surface here, and one of those lines threads it, and it has a color J, it acquires a quantum of area given by this formula here, where this is a Planck length, which is 10 to the minus 33 centimeters squared. So this is a polymer geometry, and we get the continuum geometry only as an approximation. For instance, if this surface here were such that this line doesn't thread it, it would have zero area. Now you would say, how could a surface have zero area? Well, that will be a heavy quantum situation, a very unlikely thing we'll encounter in an everyday life. An area like this table I'm sitting at typically would have 10 to the 66 centimeters, or 10 to the 66 lines per centimeter square in it. So there were a huge amount of lines, and therefore the area of the surface for all practical purposes is continuous. Because if I move the surface around, yeah, I'll grab another line here, I'll lose a line there, but any movement will be, gazillion lines. So the whole motion would look smooth. It's only if I were to shrink my table to 10 to the minus 66 centimeters squared that I would encounter a heavy quantum situation like this. So there are novel features that emerges. Now, everyone over the years always conjectured that in a quantum theory of gravity, areas were going to be quantized. And the obvious thing was going to say, well, they'll be proportional to the Planck length squared. Because again, we said the Planck length is the natural length that appears when you combine G, C, and H bar, okay? So it's the natural length that appears in the constants of your theory. So the natural thing was to say, okay, your quantum of area is going to be proportional to the Planck area squared. No one doubted that. But there's a very specific way in which loop quantum gravity says the quantum of area emerges that no one had conjectured before. The eigenvalues, as you see, are not equally spaced, but actually they actually crowd other in a rather sophisticated way, and they imply that the geometry is quantized in a specific way, and it's a very reasonable specific way because the eigenvalues crowd up very quickly, meaning you're only in the quantum regime really when you're close to the quantum scale. As soon as you move out, 10 Planck lengths and so on and so forth, you immediately go into the continuum regime. So using these structures, and there's similar operators that people introduce for the volume of space and so on. They're a little bit more complicated, so I'm not going to discuss them in detail here. But essentially, using these structures, in 1996, Thomas Thiemann was the first to write a non-trivial, mathematically well-defined, finite, anomaly-free theory of quantum gravity, including coupled to matter. Basically, what he had done is he took the Einstein equations and he put a hat on top of them. He made them quantum. So the Einstein equations normally say that the geometry is equal to the matter. This is the matter content, the stress energy tensor. Newton's constant is between. And what Thiemann showed us how to do is to put quantum hats on both sides and write a quantum versions of the Einstein equations that was well-defined mathematically, meaning there were no infinities anymore. It was non-trivial. I mean, it's easy to write equations that are non-trivial, that are mathematically well-defined. You know, I could say, well, this is 0 and that is 0. Yeah, sure, that's mathematically well-defined. It doesn't have any infinities, but it doesn't have any physical contact. What he showed is the way he did this is a very complicated equation here on the left and the right. So it's a non-trivial theory, but yet there are no infinities, it's finite, and it's anomaly-free, which is another problem that quantum theories usually have. So you might say, are we done? Did we quantize gravity? Well, we don't know, really. It turns out that it's very difficult to get physics out of this theory. Now, why is that, you might ask? Well, these type of theories that we're talking about are fairly complicated. For instance, consider quantum chromodynamics, the theory that describes the strong interactions. Now, that is a theory that we don't completely control. We know how to do some calculations in QCD using what is known as lattices, putting the theory on a lattice and putting them on a computer. We also know that in certain limits, that theory has what is known as asymptotic freedom that allows us to do perturbation theory satisfactorily. Well, none of those two things seem to work in gravity. So in QCD, we can't get all results we want from the theory. People are still fighting hard to get things like the mass of the proton to great accuracy and so on, because they really have to put a lot of effort into those lattice calculations. Well, here, we're a step back. We can't even do that. So it's a complicated theory, and we have a hard time getting physics out of it. Now, there have been some results for black hole entropy that I'm not going to discuss, but they do not probe the entire theory. They only probe certain aspects of it. So what people are trying to do is to probe physics in situations that are simplified a lot by symmetries, such that you can make some progress with this theory. And the two examples I'd like to discuss in this talk that are cosmologies and black holes, spherical symmetry, are places where people are making some progress of that sort. Before I go into this, so if you want to learn everything you want to know about this, Thomas Thiemann has a book in Cambridge from 2008 where he explains all this. The book is thick and not an easy reading, but you know, if you go slowly, it's very well explained and you can make through as many details as you want. Before I go on to applications, I'd like to point out that there's some controversies concerning this theory. If you go on the internet, you're going to find blogs and other places where people say all sorts of negative stuff about quantum gravity. They say the most crazy things. They say that, you know, people work in this field are crackpots, they don't know what they're doing, it's all wrong, etc. I don't recommend you go on blogs to look about this because a lot of the opinions are hastily put out, they're not well thought through. Most of these people have not studied this in detail, so the criticisms sort of miss the mark. Fortunately, if you want to learn about the controversy, there are a couple of academic papers about it. Hermann Nicolai, who is a well-known string theorist at the Albert Einstein Institute in Germany, took the time to take some time off and study loop quantum gravity in detail and wrote an academic paper in classical and quantum gravity with these two collaborators and also a lecture note in physics where he levies the criticism, the academic criticisms of the theory. And Thomas Thiemann was able to respond in the same issue of lecture notes in physics. Unfortunately, these are technical papers, but if you want to get into the meat of the controversy, you really need to get into the details, unfortunately. I can only give you a sort of general picture of what the problem seems to be. So the main concern a lot of people have are that these spaces we're using, that inner product I introduced, although it's mathematically precise, is not traditional, is not what has been used in other theories of physics. The properties of these inner products appear rather counterintuitive. They seem to be overtly discontinuous and so on. On the other hand, For like 50 years, people have tried the traditional inner products of quantum field theory and got nowhere. So something had to give in order to make progress. People who work in this field feel that, well, this is a place where something new is introduced and it allows us to make problem. Other people outside the field might feel, well, that's a step a little bit too bold. That is too different what has been done. And by the way, it's completely okay when science is incomplete for honest scientists to have disagreements about what is the most promising avenue of research. It's different when you have a scientific result. If you have a scientific result, you can say it's true or it's not true. You can check it against nature, against experiment, and so on. But when you're in the middle of a calculation, honest scientists can say, look, I don't think it's going to work that way. Another one say, well, let me try it, okay? So that's the kind of disagreement that is taking place here. Some people say, well, can you use this in other examples? Can you use these type of techniques to do Maxwell theory, to do the harmonic oscillator, and so on? And people have taken the time to actually do this. And they have shown that indeed you can describe ordinary Maxwell theory, the ordinary harmonic oscillator with these type of techniques, but they don't look pretty. The normal states that people discuss, when you frame them in type of these states, are complicated, ugly superpositions. Now, the insiders say, look, these techniques were designed for something like general relativity, which was invariant under diffeomorphisms. All these other theories aren't. So it's not surprising that the techniques that work well for one theory fail for the other. Remember, all the techniques that work for the other theories fail for general relativity, okay? Now, unfortunately, this leads to an impasse. The insiders say, see, we did it. The outsiders look at it and say, see, but it's ugly, okay? And that essentially examples were never convinced critics. So the ultimate question, though, is what we were talking about before. Physics is about nature. Does the Feynman Hamiltonian contain the correct physics? And for that, I'd like to move to the final part of the talk, which is applications. So the first application I'd like to describe is cosmology. Now, cosmology is the study of the universe as a whole. Now, you might say, how do you study the whole universe? Well, very coarsely. Essentially, you ignore most of the degrees of freedom and you concentrate on a few and try to explain their behavior. Now, in general relativity, there are fairly general theorems due to Hawking and Penrose. Penrose got the Nobel Prize in part last year because of these theorems that say that space-time becomes singular at some point. In cosmological settings, typically you assume the metric is very simple and you concentrate like homogeneous and isotropic, meaning it looks the same everywhere and it looks the same in every direction. The only non-trivial components are the scale of the space-time, which is just a function, a single function of time, okay? It tells you how big the universe is. The volume goes as a cube of this, and the curvature of the universe as its inverse. Now, we know the universe expands, so if I run it back in time, the universe contracts. Eventually, it contracts down to a point where the scale factor is 0, and the curvature blows up. At there, the classical equations stop, because we have what is known as singularity. Things blow up, become infinite, and the equations can continue. The general expectation is that this is not what happens in nature. After all, in nature, nothing is ever infinite, nothing is singular. The general expectation was that when you went so close to the origin of the universe that everything gets concentrated into a point, you went beyond the realm of applicability of the theory, and you had to have introduced quantum effects. At small sizes, curvatures are very large, energies are huge, and therefore it's not reasonable anymore to say, well, gravity is macroscopic. You really need to throw in quantum mechanics. And after all, something relatively similar happens in ordinary quantum theory. The Bohr atom has an electron that classically should start decaying because it emits electromagnetic radiation and eventually crashes against the nucleus and produces a singularity. That is not what happens in nature. Quantum mechanics tells us that there actually is a ground state. There is a minimum energy that is given by the ground energy of the hydrogen atom. Does loop quantum gravity predict something similar near the Big Bang? And the answer is yes. But before I tell you the answer that loop quantum gravity gives you, let me tell you what the situation was before loop quantum gravity. So what was the usual story before loop quantum gravity? I mean, people have been looking at this for many years. Well, since you're studying just one degree of freedom, a function of time, this is not even a field theory, right? This is a mechanical degree of freedom. Okay, it's just a function of time. So obviously we can quantize this. We can promote this to an operator acting on states that are functions of the scale factor multiplicatively, and so on. An ordinary quantization, just like you do for the harmonic oscillator, can be done for the universe when you're looking at so few degrees of freedom like this. The Einstein equations become a simple ordinary differential equation, which is known as the Wheeler-DeWitt equation. This was studied extensively in the 70s and 60s, and the conclusion was that this quantization does not resolve the singularities. And since the 1970s, this created an impasse, because you're dealing with a quantum theory, a quantum mechanical system, rather than a field theory. There's no wiggle room. In quantum mechanics, there is a theorem known as Stone-von Neumann theorem that tells you that once you have a quantum representation for your theory, you're done. Any other representation is equivalent. So there was no change of variables or things that you could do that would fix the problem. There's no place to escape. Loop quantum gravity, in this sense, is a game changer because it violates one of the assumptions of the Stone-von Neumann theorem. I don't think you want to know all the details, but if you want, this is a Stone-von Neumann theorem, and this hypothesis here, this weak continuity, is violated by that inner product we introduced. Remember when we had two loops that looked the same, but the inner product was zero because there's a little difference? Well, that violates this hypothesis of the Stone-von Neumann theorem. So it allows to introduce a new quantum representation that has different predictions than all the other ones. And so this is a prediction of loop quantum gravity. This is the volume of the universe as a function of time. I don't know if you can see it, but there are two things here. There are the quantum results in red, and there are the classical results of general relativity in green. If you have a large universe where we are today, both of them agree exceedingly well. They both say the universe will start contracting. But if you get to very small universes, general relativity keeps on contracting to zero and produces a singularity, whereas loop quantum gravity achieves a minimum size of the universe and bounces back. So what loop quantum gravity tells us is where we would have expected the Big Bang in general relativity, you get what is known as a big bounce. The universe achieves a minimum size, Planck size. Curvatures are very large, but they're finite, and the universe bounces back to a previous universe that is classical. So this shows that loop quantum gravity actually solves the singularity in cosmology that other quantizations before could not solve. Now, a lot of people say that, look at this and say, well, yeah, you solve the singularity, but all this is just math, right? I mean, here the energies are so large that if it was a Big Bang there or there was a bounce, we're never going to be able to tell, right? We can't probe the universe there. That is true. We can't probe the universe so close to the Big Bang to tell if this or that happened. But it turns out that you can get kind of close. To do that, what you need to do is you need to take that space-time I discussed and put some perturbations to live on it and study how some fields living on that cosmology behave. And you try to see if out of that you get the spectrum of the cosmic microwave background and compare it to experiments. Now, how, you might say, why is quantum gravity relevant to all this? I mean, the cosmic microwave background is created long after the Big Bang, when curvatures are very small, when quantum gravity is not terribly relevant. Indeed, quantum gravity is irrelevant before and after inflation, when all these perturbations of the cosmic microwave background get formed. But however, it influences the initial states for the quantum fields. That inflation later turns into the spectrum of the cosmic microwave background. Let me tell you the story for that, the traditional story before loop quantum gravity, because it's really cool. This is a traditional story. Instead of a bounce, people have the Big Bang here, and they have this period called inflation, where the universe expands exponentially. Now, what they do is before inflation, they put a quantum field here, and they put it in the simplest possible state, the vacuum, with no excitations. Then they evolve that quantum field, and they study the correlations of the field up here, and they discover that by evolving it through inflation, the correlations up here are non-trivial. The vacuum state changed into a different state that has non-trivial correlations. What do I mean by non-trivial correlations? Well, you have probably seen this picture of the cosmic microwave background, right? This is the differences in temperatures, which are tiny. I mean, this has been blown up by 10 to the 5 in order to be able to see any differences in colors there. But essentially, the cosmic microwave background is at a uniform temperature with minute differences on them. If you look at the picture, you might think, well, this looks like randomly distributed, but they're not. It turns out they have correlations in between them. The way you check for the correlations is you look for some direction in the celestial sphere, and then you look at another direction, say separated by some angular separation, say 30 degrees, and then you sort of sum all the temperatures at the same angular separation. And if this were a truly random field, that sum would give 0, okay? If this were random, they would randomly cancel out. But it turns out that they do not. If you plot that thing I just told you as a function of the angular scale, this is just another way of writing it. This is a function of angle, and these are the fluctuations that sort of sum I told you about. There's a distinctive structure here. This is not non-zero, but it has a very distinctive structure. This plot has this green curve is the calculation coming out of traditional inflation, the result of taking the vacuum and evolving it up to there. And these red dots are the experimental measurements. And as you see, the agreement is spectacular. So this is the great triumph of inflation, of traditional inflationary theory. Now, what does loop quantum gravity change in all this picture? Well, loop quantum gravity says that, look, why are you going to put the vacuum state at the beginning of inflation? I mean, why is it special anything there to put it? If you're going to put the vacuum state anywhere, well, you ought to put it here at the bounds. That's a special point. That's the point of symmetry of the universe. Or perhaps, if you don't like that, you should put it at the very past of this previous universe. Turns out it doesn't matter too much if you do any of the two. The important thing is that if you put the vacuum here or you put it back there, when you evolve it, by the time inflation starts, you're not in the vacuum anymore. And therefore, the correlations that you get at the end of the day are not the same that you get in ordinary inflation, but you get corrections to them. The corrections are plotted here. This is the same thing as before. This was the upper coordinate. This is large angles here, small angles there. This green thing was traditional inflation. Loop quantum gravity produces this jittery curve. That's normal. Once you don't put the vacuum at the beginning, you get these jitters. The average of the jitters is this. So there's a little difference at large angular scales. Now, if we go back to the previous plot, large angular scales is here. And as you can see, the experimental points have a lot of error too. So the reality is loop quantum gravity disagrees with traditional inflation down here, agrees all across this. And unfortunately, at the moment, the experimental values don't have the accuracy to tell one theory from the other. There's also a difference in an equation that arises in inflation called the consistency relation. This is an equation that relates two properties of that cosmic microwave background. This is the so-called power spectral density. This is the spectral density of the tensor perturbation. These don't matter. There are two numbers that you compute on that spectrum that ordinary inflation say they have this relationship, a factor of -8 between them. Loop quantum gravity adds a correction to them. Now, these numbers have not been measured yet for the cosmic microwave background. There are bounds on them, but there are no definitive values. This could change in the next few years, few meaning 5 to 10 years. When these numbers are measured, if there is a -8 relationship between them, then it looks like the corrections of loop quantum gravity are not there, and the theory would be disfavored. If it doesn't give 8, it would suggest that traditional inflation isn't getting the picture right, and loop quantum gravity might be more favorable to this. Okay, so this is the closest we are right now to having an experimental prediction of the theory. Let me water down that a little bit. It's really not an experimental prediction in the usual sense, because it's very difficult to make unambiguous predictions for the whole universe, because there's always initial conditions. This whole thing here, which I didn't give you the details out, is related to the value of the field that generates inflation at the bounds. And that's a free parameter of the theory. So in principle, you could play with that parameter and make this go away. So it's not an unambiguous prediction of loop quantum gravity that this factor is going to be away. It's going to be there. To make it go away, you have to choose an unnaturally large value. There's no reason why it should have a large value, that inflaton field at the bounds. So I still believe that if we get 8, loop quantum gravity is disfavored. You could make it fit, but it would be very unnatural. Similarly, traditional inflation is not a single theory. There are many models of inflation. You can do multi-field inflation. You can do all sorts of things. And they can also get different predictions for this. So again, it's very difficult to get a prediction for the whole universe that is unambiguous. You can just get models that are a little bit or a little bit less favored by the data, and that is the situation here. Let me move on to the second application. I wanted to talk about black holes. Black holes are about, and not necessarily, but we're going to study them in the context of spherically symmetric gravity. We're going to assume that things are perfectly spherically symmetric. Of course, black holes in nature and reality are not perfectly spherically symmetric. Black holes rotate and so on. But there are many black holes out there that are reasonably approximated by a spherically symmetric distribution. So as a first crack to the problem, we study the spherically symmetric ones. What are black holes? Black holes are regions of space-time where gravity is so intense that nothing can escape, not even light. Black holes were actually discovered pretty soon after general relativity was introduced. Einstein introduced his equations in November 1915, and the German astronomer Karl Schwarzschild found a solution with spherical symmetry that actually describes black holes correctly in March of 1916, 3 months later. But actually, although a solution is deceivingly simple, we can write in essentially one line, it was not properly understood until the 1960s. The fact that the space-time is curved and the fact that the space-time is so curved in a black hole makes it much more difficult to understand that a simple one-line expression for the geometry might convey. The best minds of the 20th century physics, Schrödinger, Heisenberg, Eddington, Weil, all died without understanding what that metric meant, the Schwarzschild metric. Schwarzschild died actually just a few months later. This was actually quite meritorious. Schwarzschild was fighting in the Russian front with the German army when he solved the Einstein equations in his sort of notebook, and he was very sick with an illness that killed him in May of 1916, a couple of months after his solution. So all those great physicists died without understanding this solution. So I want to caution you that although we can write it in one line, it took like 50 years to understand properly. So what does the solution describe? Well, the idea is you have a star. The star exhausts this nuclear fuel that was what kept it afloat. And then its gravitational field pulls it and makes it smaller and smaller and smaller, denser and denser. Gravity becomes more and more intense. Now, the matter that collapses to form that black hole, so the star collapses, gravity becomes so intense that light cannot exit anymore. You form a black hole. The star keeps on collapsing. And eventually, in the interior, it collapses down to a point fairly similar to what we had at the Big Bang. Densities become infinite. You have a singularity. General relativity stops being valid. Is that fixed by loop quantum gravity like the Big Bang was? Well, the answer is yes. With my collaborator Gambini in 1913, we were able to actually get in loop quantum gravity to where Schwarzschild got in 1916. Okay, so essentially we are in this field where they were in 1916. We were able to solve the theory, the Thiemann equations, in closed form for spherically symmetric vacuum quantum gravity. So essentially we are where Schwarzschild was in 1916. We have the exact solution of the Einstein equations in spherical symmetry, and the singularity is eliminated just like it was at the Big Bang. You can go through the region where the singularity used to be and move into the future through it. For those of you who saw the movie Interstellar, you might remember that the astronaut goes into the black hole, gets through the singularity, and travels into the past. Well, travel into the past is really bad because it creates all sorts of problems. So the reality that we have here, when we find the solution that describes that situation, is, well, if the astronaut had been Planck scale, because before that, a regular astronaut will be torn apart by tidal forces, but if you had been very tiny, you had moved to that region of very high curvature where the singularity was to be, but you just continue living into the future of your space-time. So there's nothing funny going on there. Unfortunately, a journalist and New Scientist, when we presented this paper, misunderstood the statement. The journalist said, you enter into another universe, and drew this picture here of someone jumping into another universe, which I just told you is incorrect. And this sort of broke the internet. There were hundreds of articles written claiming that loop quantum gravity sort of says that black hole is not infinitely dense. There are portals to other universe. And although this was from 2013, you can see that in 2020, there are publications that keep on sort of quoting this incorrect interpretation of our results. Anyway, we can do some more things with black holes. You probably have heard that Hawking told us in the 1970s that black holes emit particles. This phenomenon can be studied in loop quantum gravity, and you get conclusions similar to Hawking's. We can study the Casimir effect between two spheres surrounding the black hole. This is a nice calculation because the Casimir effect between two surfaces, of course, can be computed in ordinary quantum field theory, but the infinities appear, and you need to regularize and renormalize. In this case, the discreteness of space-time makes the calculation completely fine, and you just need to sum the energy and see how it changes with the separation of the plates, and you get the Casimir force. Investigations now continue trying to understand how Hawking radiation could lead the black hole to evaporate. This is the holy grail of fundamental theoretical physics. Neither string theory nor loop quantum gravity has the answer yet. Hawking's calculation just assumes that particles get emitted. It doesn't explain how they got emitted out of the black hole, how the black hole shrinks and loses energy as it emits particles. That is what all theoretical physicists are behind, trying to understand how that calculation could work. And neither us in loop quantum gravity nor in string theory have the answer, and we're working hard on that. Let me conclude here. So as I argued, loop quantum gravity is an approach to quantizing the geometry of spacetime. It is based on new mathematics that may break long confronted logjams of the field. There are skeptics about the approach. As I said, the new mathematics not everyone likes it. There are some physical results that are starting to emerge in situations of physical interest, some that might have some confrontation with experiment not in the distant future, and research is progressing apace in the field. In addition to that book that was mentioned in the introduction, more recently, Gambini and I have introduced two different books. This one is from 2011. This one is for students that are undergraduates in physics. It has formulas, but it starts from scratch. The learning curve is steep, but you can follow it. And if you want a more popular book with no formulas, this is from last year. This is really only like less than 100 pages long. You can take it to bed at night and read it in one sort of reading, and it will give you an insight into what is going on in the field without having to go into the details. Thank you very much.
Yeah, thank you, sir, for your nice presentation, sir. So we have one guest with us, Sudeshnu Theory. So I can join him. So can you listen us?
Yes.
Sudeshnu? Okay, so I have got a question. So the first question is, what is the quantized space-time?
So a quantized spacetime is a quantization of these geometrical variables that describe spacetime, like quantum areas, quantum volumes, that in some semi-classical situations will approximate a spacetime like we're accustomed to seeing.
Okay. And another question is, what is the loop quantum gravity?
So loop quantum gravity is what I described, is the idea of applying these loop variables to describe gravity and to describe the quantum theory that results.
Okay, thank you, sir. So we are very grateful to you that you have given us time for our International Physics webinar. So I'm sorry that we have disconnected from Facebook after 20 minutes. So that's why most of our students cannot ask questions.
I see.
So yeah, thanks again, sir, for your nice presentation.
Okay.
We would like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology. And we have one question before ending. Our
Yes.
guest, Sudeshnu's Theory. What are the future endeavor on LQG?
Like I said, there are people pushing forward in cosmology, trying to get other predictions like non-Gaussianities of this cosmic microwave background that could be observed. People in spherical symmetry are trying to push to understand how a black hole evaporates with a Hawking process. And there are other people trying to understand how to describe the theory better at a more fundamental level, using the language, for instance, of path integrals, which is a different way of seeing quantum theory that has been very successful in particle physics, and people are trying to import into this approach.
Okay, sir. Thank you.
Okay, thank you very much for the invitation.
It's our pleasure, sir. Bye for today.
Bye-bye.
And hopefully in near future we'll announce another webinar with you, sir. Bye for today. Good night.